So you'll never be out of questions to do this for this topic. You've got like 25 years of past papers. Motion in gravitational fields. Okay, as usual, I'm going to go things by first principles because I don't like the idea of teaching things. Now, I don't know if you guys have had much on the solar system, but we did when we were in year 11, and I think that's been removed from the syllabus. So, brief history of the solar system. Okay, I'll ask you guys how much you know. Sana, can you tell me something about the solar system? Anything?
Like anything like about the solar system?
Yeah, anything. What do you know about the solar system?
There's the sun that like is basically holding the whole solar system together.
Okay. I swear that could be like a physics question on its own. Analyze this statement. It's true. So the sun is at the center of the solar system, not necessarily holding it together. It's the attraction between the planets and the sun that's holding everything together. Okay.
Yeah.
So yes. So in terms of the history, you need to know. There were the ancient Greeks. They also all the ancient civilizations thought that we had a geocentric model. Geocentric means that the Earth is the center of the universe, basically. Okay, how does this model work? Well, you get all the planets and stars orbiting the Earth. They go around like this clock. If this is the Earth, you can see how the planets will just rotate around. And the main guy who was able to do a lot of the astronomical calculations was Ptolemy. His work was so influential for 1500 years. Everyone used his calculations with the stars. They were so accurate, you could tell directions, you could tell everything. Okay, so based on his calculations, what we worked out was the motion of the stars and planets. Okay, as they, in brackets, in inverted commas, as they orbit, I should say. They don't actually orbit, but in his model, they did orbit the Earth. There were just minor issues with this model. So I don't know if you guys ever heard of it. If you're into astrology, have you ever heard the term your Mercury is in retrograde or Venus is in retrograde? You guys ever heard that term?
No.
No? Okay, it depends. Some people are into astrology. In order to account for all the planets going around the Earth and not around the sun, some of the planets had to switch directions. So that instead of going like this, there'd be times, based on Ptolemy's calculations, when the planets would appear to go in the opposite direction. And that's obviously because if you're going around the sun and instead you're taking the Earth to be the center of the universe, you're going to get a lot of discrepancies. So his model was very complex. He had things where instead of going like this, you'd have a spiral sort of motion, and it worked. It worked perfectly. But then came along a couple of people who suggested that the geocentric model doesn't in fact work. So there were things wrong with it. It was too complex. There were things going in opposite directions when they required. There was a lot more stars, and some of the moons that they worked out were actually orbiting planets. So, Jupiter has like 60 moons or something. So in came Copernicus, and he proposed the heliocentric model, which is the model we use currently. Okay, heliocentric means the sun is at the center. Now, because of him suggesting the sun is on the center, in his explanation, it worked so perfect. The planets were in circular orbits around the sun, and it made all the calculations a billion times easier. But the issue was, well, he was kind of persecuted by the church and stuff, and I think they killed him or something. Because you can't just propose that the sun is the center when in fact the Earth is the center of the universe. It's a very controversial topic. Okay, even though it made the calculations easier. And this is Copernicus. And then you're going to learn about one dude who discovered the telescope. Do you guys know?
I forgot.
Anyone? Orbis?
No, I forgot as well.
Galileo. Galileo. In comes Galileo. So these are the main guys: Galileo, Copernicus, and Ptolemy. Galileo was the one who discovered the telescope, and with all the stuff he did with the telescope, he was able to definitively prove that the sun is at the center, just based on all the things he saw. There were a whole heap of things we had to memorize back in year 11 about this. You don't really need to know, but he kind of provided so much evidence for the heliocentric, I shouldn't say discovered, I should say invented, because you can't discover a telescope. So it was Galileo's work. By inventing the telescope, he provided a lot of evidence supporting this model. And after his work, people could not go back to the geocentric model. And so in the end, it was sort of, you had to concede that, well, the sun is the center. And then came a couple of people who worked on Galileo's works. Okay. Although he did a lot of work in moving with models and stuff, he wasn't really interested in how the planets worked. He didn't pursue that any further. Then came in Kepler's law. This guy, he took Galileo, he was inspired by Galileo, and he really wanted to work out the planetary system around the sun, how they work mathematically. And so it's his calculations that were able to determine their positions and everything. So he did a lot of calculations, and we're going to talk about his 3 laws of planetary motion, which is what he developed. Planetary motion. Okay. And he was able to work out positions, orbits, periods, everything of the planets of the solar system. Okay. So that's where your year 12 comes in, with Kepler's laws and the work he did being inspired by Galileo and Copernicus. Okay. Sounds good. He was also helped by a few other people, and he determined a couple of things which didn't fit Copernicus's model, because Copernicus actually proposed that there were circular orbits. Keep that one in mind. Okay. So, any questions about the brief history lesson?
Nope.
Makes sense? Now we're ready to begin. So, yeah, I don't know. We used to have a history question back in the old syllabus. You can see why the old syllabus was dodgy. We had a lot of useless questions, if you will. So let's go through Kepler's laws of planetary motion. I reckon we'll start this. Kepler's first law, the law of ellipses. Now I'm going to ask you guys a question. What is an ellipse?
Oh wait, ellipse. Isn't that when like the sun or the moon or something like that is in front of each other or something?
That's eclipse.
Oh, okay, yeah, no.
Nah, wrong thing. Let's go on to, okay, here's a simple thing, because you haven't learned it in maths, but we'll do it anyway. So I'll compare 2 different shapes. I'm going to try my best to draw this. What shape am I trying to draw here? It's all right, I guess. It didn't draw too bad, but what is the shape on the left?
A circle?
It's a circle, good. A circle, if you remember, if the planets were going in circular motion, as we've done so far, they'd be at a position here. We'll call this P, the planet. And the sun would be here. And the way it would work is that the planet and the sun, they would be equidistant. So the planet would always be the same distance from the sun every single point in its orbit. Do you get the idea? So this distance will be the radius r, and it would not change as the planet goes around the sun. Okay, and we can represent this mathematically, if you remember, by the equation x squared plus y squared equals r squared. You must have done this in maths, at least in year 10, if not in year 11 and 12. Now the ellipse is a circle which has been dilated or squashed. Now I think in 3-unit maths there's a topic called dilations. I don't know if 2-unit students do dilations. Have you done it, Sana?
No.
No, it is. I remember it's in the textbook. But the idea for a dilation is compare y equals x squared to y equals to, let's say, x squared on 4. Can you explain the difference between these two? Think logically. I'll sketch them out afterwards. So if we were to sketch it out on the plane, y equals x squared would be, well, it's a nice parabola. Oh, that parabola. And how would you compare that to y equals x squared on 4?
Isn't it more narrower because the smaller it is, the narrower it gets?
Be careful, this is on the bottom. This is dividing by 4. So if this was, hypothetically speaking, a 0.8, it would now become a 0.2.
Okay.
So what is it actually happening? It becomes extremely flat.
Okay.
You can see that. I think what you're thinking of is y equals 5x squared or something. In which case, to make this blue, it'll become extremely steeper, like so. That's the concept of
Yeah.
dilation, squashing things and moving things around. So what's done in an ellipse is that the x is squashed and the y is squashed. Both are squashed by a factor. So I'm going to rub this out now. So the equation of an ellipse mathematically is like so. X squared on a squared plus y squared on b squared equals to 1. That's the equation of an ellipse. And back in the old days with the conics was in 4-unit maths, this used to be the equation we used to use. Okay? What I want you to understand is that the x has become dilated, it's become squashed. The y has become squashed. And then in order to divide everything across, we sort of just divide by a squared b squared. So it becomes a 1. And you can try sketching this on any like Wolfram Alpha or calculator you want. And the shape of an ellipse is an oval. So you know how we used to call things an oval back when we were small? An ellipse is a squashed circle, like so. Okay? It's got x here, y here. If we wanted to work out the intercepts, we could from this equation. This would be a, this would be minus a, this would be b, this would be minus b. And again, we have 0 here, which is the center. Does that make sense?
Yeah.
Now, so I'll write this down, the explanation. I probably make this grammatically correct. And the degree of stretch, now this is a new concept, is known as the eccentricity. Okay? The eccentricity is the degree of stretch. Now, for a circle, the eccentricity, which is what I'm going to call E is 0 for a circle. It is so perfectly round and everything is so perfectly equidistant from the center that its eccentricity is 0. Okay? For an ellipse, the eccentricity is between 0 and 1. Okay? And if you are really interested in where this concept comes from, I can show you. I think the formula from memory, this is, keep in mind this was like 6 years ago. Formula was like E squared equals B squared on A squared 1 minus E squared. Oh no, that's something else. Let me quickly get the formula for you guys. Just if you're interested, eccentricity formula, how we can work out the degree of stretch. I guess it's more fun if you want to play around with it. It sort of helps you to understand. Let's see, where is that formula? E equals to, got it, I got it. Yep, it's this. 1 minus B squared on A squared. That's how we work it out. Yep, that's good. That's the formula for eccentricity. Now, why is this formula interesting? There's one reason for doing it. Because when B equals to A, which is the case for a circle, the eccentricity comes to 0. And this value cannot be bigger than 1. You can see mathematically why, because E squared is a positive number. You're going to be getting E squared equals a negative number, and you can't square root negative numbers. Does that make sense?
Yeah.
Yep. So that's how we work out that degree of stretch. This is the eccentricity, how weird it is. Now, with an ellipse, we have something called a focus. We have a focus for a circle as well. The focus in the circle is the sun. It's the center of everything. In an ellipse, the focus is off the center. And there are two foci. So plural of focus is foci. One focus is around here, and one focus is around here. So we actually have two foci in an ellipse. You can call them S or S dash. I think that's what we used to say, but I'm just going to call it focus, focus. Okay, so we actually have two foci and a center, and the planet will be here. Do you already see what's wrong with our assumption that everything is circular motion? So you can see how in the circle, all the foci, both the foci converge onto the center, whereas in an elliptical motion, you're getting the sun at one of the foci. So the sun, which I'm going to sort of highlight in yellow, is here. Now maybe I'll just do it here. Okay, do you see the glow of the sun? So Kepler's first law, can you guys hear me? Just checking.
Yep.
Yep. So the sun, this is Kepler's law now. Each planet moves not in a circle, as you've done in inquiry question 2, but in an ellipse. That's the orbit. It's an elliptical orbit. And what we can say is, with the sun at a focus. And we know that it's off the center, because the center is the middle of that ellipse. This is Kepler's first law. Okay, just like Newton had his 3 laws, Kepler has his law as well, as you can see here. And so it's very weird. The motion is, it's not going to be regular motion. If you think about it, if you're closer to the sun, that might explain why summers are hotter or winters are colder, right? Depending on where you are in position to the sun. Not only that, you tend to not have a constant motion. Do you remember in circular motion, the speed wasn't really changing, it was uniform? In circular motion, the motion is uniform. In elliptical motion, the motion is not uniform. You tend to go faster in some places and slower in other places. Okay? Do you guys have any questions so far? Anything at all?
No.
What about you, Orbis? Any questions?
No questions.
Now, there is an alternative way to draw an ellipse. I guess it's a fun fact thing. And I think this is actually worth trying because it's a fun thing when you're bored on, like, say, Saturday or something. If you wanted to draw an ellipse, you get a pencil. So this is where your pencil would be. Just draw an ellipse first. Oh, my diagrams are so bad. Let me see if I can get a shape. No, I can't find it. Insert. Whatever. Seems. If you want to draw an ellipse, this is another alternative definition for what an ellipse is. An ellipse can also be defined as the distance from the two foci is a constant. So if I have one focus here, let's make it green just to keep it the same as what we did before. If I have two foci here and I've got the planet here, another way to define an ellipse. Now we'll be coming back to this law when we learn about Newton's law of gravitation and we learn about attraction between planets. This law obeys the law of conservation of energy. Now, Orbis, what happens if I drop a ball? What energy transformations are occurring?
So gravitational potential, I'm pretty sure,
Is converted to?
Is it kinetic?
Yes, kinetic. The energy of movement is kinetic energy. Good. What you notice with this Kepler's law is that when you're in the position, I'm going to call this A, because you are further towards the sun, you've lost gravitational potential energy and you've gained kinetic energy, which is why you end up going faster or rather you cover a lot more circumference when you're at situation A. When you're at situation B, all that kinetic energy has been converted to gravitational potential energy, and you are further away from the sun. Does that kind of make sense? Do you want me to repeat anything?
Yep, I get that.
You get that or not?
Oh yeah, I'm good.
Okay, so what is the law of conservation of energy? Might have done this in year 11. Anyone?
Isn't it that energy can't be destroyed or created?
Yep, good. Energy cannot be created or destroyed. What is the second part of it?
It can only be like transformed.
Yep, it can only be transformed. Good. Memorize this one. Honestly, this is a really important one because later on when we do Lenz's law in the next module, you always come back to this law. I feel like this law is one of those fundamental things. You keep coming back to this. It can only be transformed. So at scenario A, you can perceive it as a ball falling. That's the way I think about it. Okay. And if you really want to put this in words in the explanation, at A, the planet is closer to the sun, and as it moves closer, because if you think about it, in elliptical motion, we have two parts of the motion. We have here, this is the point, I'll put here. We have a point here where you are the closest distance to the sun. And we have a point here where you are the furthest distance away from the sun. Do you see those? There's a huge discrepancy there. So what happens is, at A, the planet is close to the sun, and its radius, or rather, instead of calling radius, but its distance from the sun is actually decreasing. Yeah? If its distance is decreasing, what this tells us is the planet is losing gravitational potential energy, which you remember is like a ball falling down. And instead of energy being lost, it can't be created or destroyed. It is converted to kinetic energy, which you remember is half mv squared. And so what this tells us is, at A, the planet is moving faster, and so it can cover a greater circumference. Any questions about that?
No.
It's decreasing. Planet is losing GP, and it's being converted to kinetic energy. So it's moving faster. So you've covered a huge amount of that circumference in the same 1 month as you did at B. And at B, it's like a car going up a hill. If you guys drive, which I'm sure you do, you realize that if you don't hit the brake, if you don't hit the accelerator, and you're going up a hill, you're going to slow down, right? The planet is moving further away from the sun, i.e., it's like saying its distance is increasing. And if the distance increases going up a hill, the planet gains potential energy. Potential energy, do you remember what potential energy is? Like, do you remember how to define potential energy? Orbis or Sana? Do you know what the definition of potential
No.
energy is? Nope. And it is, I should rather say losing is probably a better word. Potential energy is the capacity to do work. Energy is the capacity to do work. Potential energy is stored energy. I thought you guys, I don't know, might have covered this in one of the recap lessons. Energy and work are equivalent, right? Those three things, it's like the congruency symbol, but energy and work are equivalent. This means is that energy is the capacity to do work. For example, if I have kinetic energy, if I'm running and I was to slam into someone, I will have the ability to do work on the object that I slam into. Okay? If I have a gravitational potential energy and I was to jump off a cliff, I have the stored energy within me to do work, which will increase my kinetic energy as I would fall down the cliff. Does that kind of make sense?
Yeah.
Energy is the capacity to do work, and it works both ways. Work done on an object changes its energy. So this is the energy and work equivalence principle. Potential, if you really want to know what it is, just keep it very simple. Potential is stored energy. Okay, my banana on my desk has potential energy. It's got chemical potential energy. That energy is stored. When I eat it, my body is able to harness that potential energy. Kinetic energy is the energy of movement. And that's because a car or anything that's moving, well, if it was to crash into something, it's got the ability to move other things. So you've done this with momentum. You've done the billiard balls. When one ball, it's got kinetic energy and hits the other ball, all that energy is transferred and now this ball moves away. So that's the idea. Kinetic energy is the energy of movement. Potential energy is the energy which is stored within an object. And often it's due to a field. Okay, often. Not always, but often. So we talk about gravitational potential energy. The only reason that exists is because we are in the Earth's magnetic field, or Earth's gravitational field, or we're in the sun's gravitational field. Now, if you look at it, we go up. In this half of the scenario here, as you can see in the pink, we are closer to the sun. And as we fall towards the sun, that stored energy, potential energy, gets converted to kinetic energy. I go faster around the ellipse. And then there's a second half here. I'm going to rub the first half away. As we rise up, as we go uphill, we're going further and further and further away from the sun. We're getting more potential energy, but we're losing kinetic energy. And this potential is stored so that when we go around the circle one more time, or when we go around the ellipse one more time, and we get to position A again, that energy can be converted into kinetic. And it's a never-ending loop. Does that make sense?
Yep.
Yep, you guys get it? No questions about that?
No.
And so another way of putting this, where we were talking about losing energy, gaining energy, is something we call orbital energy, which you will cover in probably 1 or 2 weeks' time. But the orbital energy is the sum of GPE, gravitational potential energy, and kinetic energy, and it's always a constant. If you lose one, you gain the other. If you gain one, you lose the other. That's the way it works. Okay? And so it kind of relies on this idea, orbital energy. I'm just going to highlight it for you guys. Okay? And it really helps you understand what I'm talking about, because if you gain one, you have to sort of lose the same amount. Okay, and there are many types of potential energy. I've talked about the field, but the ones you're going to be learning about is electrical potential energy, which you probably have done in year 11. I'll just get rid of this. Yeah, do you remember electrical potential energy? Yes, no, maybe? We'll be covering electrical potential, gravitational potential. Unfortunately, there's no magnetic potential. I've never seen that before. What have we done? We've done gravitational potential, electrical potential. Chemical is due to the bonds. So when I was talking about the banana, there's hydrocarbon bonds. You do this in chemistry. These bonds, if you break them, you release energy. And there's always nuclear potential energy, E equals mc squared. If you were to use an atomic bomb, it's the bonds within the nucleus that are being broken. Okay, there's a lot of potential energy here and there. Can't really think of any others, but I'm sure there's other potential energies as well. Okay, cool. You ready to move on to the third law? Yes or no? Yeah, kind of, maybe.
Yeah.
Okay, now the good news for you guys is the eccentricity for most of the planets is very close to zero. It's very, very close to zero. So for all intents and purposes, we can just say everything is circular motion. For example, the eccentricity of Earth, if you were to guess what it is, the answer would be 0.0167. That is basically a circle. Because you remember when we said eccentricity of zero means it is a circle. So for all intents and purposes, especially in year 12, you sort of just assume everything is a circle other than the first two laws. The things kind of go wrong when you go to planets such as Mercury, which is why people often say Mercury is in retrograde. That was actually on the geocentric model, but the eccentricity is relatively high, 0.2056. It's a bit of a squashed orbit. And then if you look at Pluto, which was a dwarf planet, that eccentricity is extremely high. Let me actually get the data for you. So that's some of the things that actually led to Pluto being called a dwarf planet. Let's see. Pluto is 0.24. Okay, so Pluto has a huge eccentricity compared to the Earth. Not only that, if all the planets were to orbit in the same plane, this is like, imagine this is a plane, Pluto orbits in a sort of obliqueness. This is Pluto's orbit. Do you get the idea? Everything's in one plane, everything's nice. Pluto has 122 degrees from this angle. This is 122 degrees. So there's a lot of factors that led to Pluto being called a dwarf planet. It still orbits the Earth, and often a lot of the comets you see follow elliptical orbits. But yeah, this is some of the evidence which is supporting that Pluto probably shouldn't be called a planet. Okay. I don't know, I just love giving these history lessons. I feel like they're kind of interesting why things happened. It's an oblique orbit, and its size. Everyone thinks about Pluto being a very tiny planet, so the issue is obviously with the size as well. But for all intents and purposes, all the other planets in the solar systems, you can just consider it's a circle. Jupiter has eccentricity of 0.04, very small. Okay, let's move on to the third law. This is the question. This is the law where you're going to be tested on a lot, because the first two laws were only in the new syllabus. You won't find a single mention of them before 2017. Okay, so this is where you'll find last 50 years of papers have it. Kepler's third law, the law of periods. Okay. Do you remember what Kepler did? He was using Galileo's telescope. He was measuring the time it takes for the planets to go around the sun because you can track them in the sky. He was working out the average radius. He used a lot of mathematical calculations. And he came up with a very simple formula. This is on the formula sheet. The other two actually aren't on the formula sheet. This one is. His law simply states, oh, I shouldn't say the, I should say, for all planets, the cube of the average radius. Now we're saying average radius because remember it's elliptical orbit, so technically can't call it a radius, but average radius is proportional to the square of the orbital period. We've already talked about what orbital period is. It's the time taken to go around the orbiting object, so for example the sun. And if you wanted to put this another way, r cubed on t squared is equal to k, which is a constant. Okay. How are you guys going? Not completely lost so far?
No, you're good.
No, I'm good.
And how he was able to do this? You can try any planets, any number of planets, and this relationship always holds. That's what a law is. Law is something which describes nature. Keep that in mind, okay? I'll talk about that in a sec, but keep this in mind. If someone asks you what's the difference between law and a theory, why do we call it Big Bang theory and why do we call it Big Bang law? Why do we call it the theory of special relativity or Einstein's theories as opposed to Einstein's laws? How come for Newton we call his stuff laws, but for Einstein we call it theories? Do you guys know what the difference is?
Because theories they can change, whereas laws they're the same forever.
Yep, that's the idea. Laws describe nature, and they, by the inherent fact, because I'm describing nature, it will not change. So no matter how much evidence you find, you can't refute Newton's laws, even a million years later. That stuff will stay true. But if you look at the Big Bang theory, I don't know, it was probably going to be in the news or something. They're thinking of the Big Bang theory might not be correct anymore. There's a lot of discrepancies here and there. And a lot of theories that people came up with, especially how the atom looked like, we used to think atom was like a big ball of like a billiard ball. We now know that's not true. Atom's made of electrons that whiz around. So theory it tries to explain. Do you get the difference between describing and explaining? It tries to explain observations in nature. And as we get more evidence, the theories will change because we will either support the theory or we'll go against it. Which is why, if you probably remember at the start of this lesson, I talked about the two models, geocentric and heliocentric. They weren't laws, they were theories put forward by people. They described what they saw in nature and they said, or the Earth should be the center of the universe. Or the planets go around the Earth. It works. The sun rises in the east, sets in the west. It all makes sense. It's only with further observations through the telescope that we're able to prove a theory wrong and say that, well, no, the sun is the center. Does that make sense?
Yep.
That's law versus theory. I don't know if you guys will get tested on this, but if you do science extension, this is a huge topic in that. Okay, now, we could go on to calculations for this. There's a bit of preamble. You need to learn about Newton and like how his calculations work. So for all intents and purposes, I'll go through a heaps of calculation questions for this, but I'll just tell you what K is, and then I'll sort of tell you where K came from. Okay, on the formula sheet, do you guys see this? R cubed on T squared equals GM on 4 pi squared. See this?
Wait, so is it in the formula sheet?
Yep, find it.
Okay.
Try labeling all of this stuff. What do you think these variables are? 4 pi squared is a constant. It's just a denominator factor.
Okay, I found it.
Found it? Did you find it as well, Sana?
Yes.
Good. Capital G is a new thing that we're being introduced to. This is what we call the universal gravitational constant. And if you do enough papers, you will get this value memorized. I've taught this for like a million years and it's super engraved in my mind, 6.67 times 10 power negative 11. But for now, if you were lost, you didn't know what G was, go to the data sheet, first page, you've got the list of constants, you'll find capital G there. M is the mass of the sun, or what we call the star. It's the thing which is being orbited around. Okay? It's the thing in the middle. That's the way you want to think about it. 4 pi squared is a constant. That doesn't change anything. R is the orbital radius, assuming circular motion. T is the orbital period. I'm going to change this here. And that links together mathematically what we can observe for a planet. We can work out how long it takes to go around the sun. We can measure its radius. We can measure its mass. Those are sort of the things that are important. And the mass of the planet is actually irrelevant in this. The mass of the sun is important, but the mass of the planet does not matter in any way. It does not factor into this calculation. Keep that in mind. Okay, it's not the planet. Nothing to do with the planet. If I was to go around the sun, I would still follow this law. And it doesn't matter how much I weigh. Does that make sense?
Yeah.
Now, let's do some calculation questions. I don't know why, but the textbook doesn't have too many good questions. So I reckon I'll just make a couple up and then we'll keep going through it. Now, the hardest thing about this, guys, really hard, this topic, is using your calculator. Trust me, I've got this a billion times incorrect. You have to be good at using square roots, cube roots. Don't forget the 4 pi squared. Don't forget the 10 power negative 11. There's so many areas where you can make a mistake. Okay, so we'll go through one question together and I just want you guys to put this in the calculator. Okay, we'll start off with a relatively simple one. Calculate the mass of the sun if Earth's orbital radius is, remember the Earth orbits the sun, if the Earth's orbital radius is 1.50 times 10 power 11 meters, always convert to meters, and its period is 3.16 times 10 power 7 seconds. You always have to convert to seconds. I'm going to give you in hours or days, but you have to convert into seconds. Does that make sense? Meters and seconds. Okay, I'll give you maybe 5 minutes to do this. This one's a plugging in question. I don't think really I need to go through much. Maybe the next ones I will. Let me know when you're done, right?
Okay, I got the answer. Like, I don't know if it's right. It's like massive.
Yes. How much?
So I got 6.3215066624 times 10 to the power of 37.
No, that's wrong. Maybe
That's
I
wrong?
meant
Okay.
that's wrong.
I got 2.81 times 10 to the power 15.
Also wrong. Okay, just to confirm, it's 10 power 7 here, and it's 10 power 11 here, right? Just confirming that.
Oh, okay.
Just in case you might not have seen that. Maybe try again. Just change a couple of numbers around. But yeah, you will get a huge number. I'm just saying. Planets don't just weigh like 10 kilos. You get 10 power something. Should I go through it now? Or do you guys need more time?
Oh, just a second.
Okay.
Yeah, just give me a sec.
I'm getting 2 times 10 to the power of 30.
Correct. Good, good, good. That's the good stuff. Let's do this. Okay, so the hardest thing about this is getting the formula right and rearranging it. So we've got r cubed on t squared equals gm on 4 pi squared. That's the formula. Always rearrange before subbing in. I can't stress this enough. With Kepler's laws, if you were to sub things in, things are going to go wrong. Always rearrange first. If you want to make a mass the subject, you have to multiply by 4 pi, multiply by 4 pi squared, and divide by g. That's the way it works. Okay, so that gives us a formula, m equals to 4 pi squared times by r cubed, important thing is cubed, on t squared, and you have to divide by g. So it's g times t squared. So far, so good. Haven't done any magic or anything just yet. Just rearranged it. Now, 4 pi squared, this is the time where you sub it in. Now, this is why most likely you were getting things wrong. You have to put brackets. If you don't put brackets, you've already got it wrong. 1.50 times 10 power 11, close brackets, cubed. If you just cube one of these, you're going to get it wrong. You have to cube both. You have to cube the whole thing. And then you divide by g, which you need to know the value of, 10 power negative 11. And t squared, t is 3.16 times 10 power 7 seconds, whole thing squared. And if you put this in the calculator, you should get the answer. I'm going to put in the calculator right now. Orbis, did you get this?
Yeah, I got 2 times 10 to the power 30.
Yeah, good. Yeah, this is the hardest bit. Like, honestly, it's very simple to make a mistake. And you don't even realize. Sometimes you press a button and your calculator doesn't register it. See, I've already made a mistake. My calculator says something completely different. I've got 1.33 times 10 power 19, and I figured out my mistake. I accidentally put a square instead of a cube in the numerator. Right? Also, guys, memorize the mass of the sun. It's very simple. It's very, very easy. It's literally 2.00 times 10 power 30. But often if they ask you the mass of the sun, you will kind of already remember this. Okay, and this is 3 significant figures. So don't leave it as 2, leave it as 2.00. Okay, because we were given 3 significant figures in the question. But yeah, be careful when you're doing this one. It's very easy to make mistakes with Kepler's laws.